All right, and here it is time for Exponential Functions, section 4.1, with me, Mr. Hain. All right, so exponential functions, what are they? So functions that look like f of x is b to the x equals b to the x, or y equals b to the x power. Now, there are definitely some restrictions that we're looking at when we're looking at just these. And the first is that b, or the base of the exponential function, is a positive constant other than 1. That means b has to be greater than 0 and b cannot equal 1. So x, or the exponent, is any real number. It can be a fraction, it can be a decimal, it can absolutely be a mixed number, anything at all. But it needs to be a real number, so no imaginary numbers need apply. So the next thing that we're going to look at is just some quick examples, and I'm asking you to kind of pause the video or even check in with me as I go along. Why are they not exponential functions? So y equals x squared. Why is it not an exponential function? Well, the real reason is the base is a variable. If the base is a variable, it cannot be an exponential function. Next one is g of x is equal to 1 to the x power. And you guessed it, it's because the base is a 1. It cannot be equal to 1 here. It just can't. So let's take a look at h of x is equal to negative 4 to the x power. Now this is not an exponential function because the base must be greater than 0. And finally we have j of x is equal to x to the x power. Those got a lot of problems. You guessed it, it's because the variable is the base. Cool. So now we have an idea of what exponential functions are not. Let's take a look at what exponential functions are. Let's start by examining the graphs. So first we have this green graph here, and that's where we have the base as a fraction. So as the fraction increases, as it becomes closer to 1, or as the x values increase if the base is a fraction, then the function actually decreases in value. So it becomes closer and closer, but never quite touches the x-axis. And where b is greater than 1, as x increases, as the exponent increases, the value of the function increases, in fact, increases exponentially. So here are some quick facts. Let's look at the domains for both, or where the x values can be. X can be anything from negative infinity to positive infinity. All the exponential functions pass through y is equal to 1. So right here, it doesn't matter what the value of the base is. When the exponent is 0, it equals 1. Y equals 1. So if b is greater than 1, the graph is increasing. The bigger the b, the steeper the graph. So if the base here was 9, of course this would be growing very steeply. And if the base here was like 1, it would just grow at or not 1, like 1.00001. It would grow very slowly. If b is a fraction, the graph is decreasing, and the smaller the b, the steeper the graph. So if it was, say, like 1/800th, then the value of b would drop like a rock, and that's how it would be steeper. These graphs are indeed one-to-one, so they pass both the horizontal and the vertical line test. So they and their inverse are both functions. More on that in another section. And there is an asymptote at y equals 0. We'll talk about these later, but really what I mean is that, as I spoke about with the graph, the closer and closer you get to the x-axis, they do approach the value y equals 0, but they never really quite get there. All right, so let's look at the natural base e. So the natural base e is another constant that occurs a lot in financial or biological or scientific applications. Really, it's a number a lot like pi, and it happens when we're dealing with things that grow or things that decay. So as n approaches infinity, and here you see this 1 plus 1 over n raised to the n power, that quantity raised to the n power, as n approaches infinity, the value of the function, as n gets bigger and bigger, approaches a single number e, much like pi 3.14159, etc. E approaches 2.71828. Now, I'm never going to make you memorize this number. You can use your calculator. It's not a big deal. But I do want to point this out, as we are going to be talking about things that grow and decay. So let's take a look at this first function. It's checkpoint 6. 6.4 times e raised to the power of 0.0123x. This function actually models the world population X years after 2004 at an annual growth rate of 1.23%, and that's in billions. So the initial population here is 6.4 billion people in 2004. So let's use this to predict the world population in 2050. So if it's 2050 and it's X years after 2004, then X must equal, you got it, 46. So if you plug this into your calculator, we're modeling the population of the world in billions in the year 2050, which hopefully everybody will be alive for here. And kaboom, it's 11.26 billion people. That's a crazy amount of people. All right, so let's talk about compounding interest, or really, why not to have credit card debt? So annually compounding interest, we're going to build up to compound interest here, but annually compounding interest is represented by this simple equation. It's the amount of money that I put into the bank plus the amount of interest that I earn in that year. So A is the accumulated value, or how much it's worth after its period of interest. P is the principal, and here it's a very financial term. Principal means the amount of money that we first put into that account or into that annuity. And R is the annual interest rate. And looking at this, we can kind of create a table here to examine what the time in years does to an accumulated value. First, we have 0 years. Of course, your accumulated value is just equal to the principal. The second that you put the money into the bank, it's just worth that much money. So after 1 year, if we factor the P out of this equation, we actually just have P times 1 plus R. That's for 1 year of value. For 2 years, we're going to be actually multiplying times 1 plus R times 1 plus R, or really here, we raise 1 plus R to the second power. Now for 3 years, you see that we have this same period 3 times. That's what we're multiplying to find the value. And that's not changing the principal, is changing how much interest we're earning on that. And of course, the multiplier, or the exponent here, is to the third power. To the fourth means, of course, we don't have to write this out 4 times, because now we see the patterns. 1 year, the exponent is 1. 2 years, the exponent is 2. 3 years, the exponent is 3. Or 4 years, of course, the exponent is 4. Now, the real question comes when we have n years. And when we have n years, of course, the exponent is n. Now, this kind of leads us into a discussion of what it means of what if there are more periods in a year than one single term that we earn interest. And of course, this is more like what we see in our day-to-day experiences with banks and or credit cards. So the interest, or I, is going to be the rate divided by the number of periods, and it changes our initial formula for calculating interest to the accumulated value is equal to the principal times the quantity 1 plus the interest rate divided by the number of terms raised to the product of the number of terms times the years, which is T. All right, so let's look at this. If we're looking at this, semi-annually would be 2 terms. That's twice a year. Quarterly would be 4 times. In this case, bi-monthly is not twice a month. It's actually every other month, and that's a very specific financial terminology that this textbook uses, that we're using for our homework. And monthly, of course, would be n equals 12 for the terms. I can't spell, but hey, n does equal 12. So, but most banks and credit cards use continuous interest. Now, there are annuities and investment options that use semi-annually, quarterly, bi-monthly, and monthly terms, as well as twice a month and other kinds of number of terms per year. But again, most banks calculate your interest using continuous interest. And of course, that would push n, or the number of terms per year, to infinity. And if we look specifically at just this part of the equation, 1 plus r over n to the n, really that part becomes the natural base e. So we can use that to rewrite our equation for accumulated value for continuous interest as accumulated value is equal to principal times the natural base e raised to the interest rate times the time in years. All right, so how can I ask you questions about these? Well, I'm going to have you compare investments. So let's take a look at comparing investments. You have $10,000 to invest. Of course, this is a dream for everybody. You can choose between two investments. The first investment here is going to be 7.5% interest compounding quarterly, and that's a 5-year term, or 7% continuously compounding interest at a 5-year term. So here we see, even though I have a fewer number of terms within a year that I'm compounding the interest rate is a lot higher. Now, banks will often do this to encourage you to leave your money in the bank. And also here we have continuously compounding interest, and they can lower the interest rate because, of course, if they show you that interest compounds, every single infinite fraction of a second, it sounds more inviting. So take a moment and think, which one of these do you think will turn out to be better? So let's do the work. So we use our periodically compounding interest formula, and we plug in the values. P is our principal, which is 10,000. Our interest rate here is, again, expressed as a decimal. Now, this is the most common mistake that I see, is when people do not write this as a decimal. Now, they'll just do 7.5, and you'll end up with a gigantic amount, because what you're doing is you're multiplying at an interest rate of 750% if you don't convert this percent into a decimal. So make sure that you're converting the percent to a decimal. And here, of course, when we plug this in, we get $14,499.48. So at a continuously compounding term, our interest rate for the same term at a slightly lower percentage of interest, we use our continuously compounding formula. And we see that we plug it in. And again, we're converting the percent into a decimal. Must do that. You don't want a 700% interest rate. That'd be fantastic. Drop everything, invest your money there. You want to convert the percent into a decimal. At 5 years, in our calculators, it is $14,190.68. Now you see here the difference isn't massive, but it is sizable. I mean, I would rather have the $14,499. And again, even if it's just pennies off, we're going to always make the decision that yields us the largest amount of money. And this is the easiest real-world application that we have to comparing investments and using exponential functions. So I'm going to come back to this a lot. So we're going to see which one of these is better. And of course, the quarterly compounding annuity is the better choice. And that'll bring us to the end of our discussion for exponential functions, or section 4.1, with me, Mr. Hain.